All right, so for the circuit shown below, determine the equivalent resistance, the current in each resistor, and the voltage drop across each resistor. So here we have a complex circuit. So the first thing we want to do is recognize some pieces of the complex circuit as either being in parallel or in series, and then simplifying it until we get to a nice simple circuit. So what I see right here is two resistors that are in parallel. Well, now I need to go ahead and try to combine those two resistors to see what their equivalent resistance is. And then when I redraw it, I'll just draw it as one, okay? So I want to find the equivalent resistance of the 3 ohm and the 25 ohm. And because they are in parallel, I need to say that the equivalent resistance, or 1 over the equivalent resistance of the 3 and the 25, and it's going to be when we add 1 over because they are in parallel. So we're going to add 1 over 3 plus 1 over 25. Now you can go ahead and just type it into your calculator, make them decimals. If you do make them decimals and type them in, then keep like 4 or 5 decimal places until you get to your final part for finding the equivalent resistance, and then you can round it to 3, okay? Now when I did this, I left it and I just went ahead and found a common denominator. So I said the common denominator was 75. So equals, I don't know what I was doing there. So 3 times 25, so it would be 25 over 75. And then 25 times 3, so it would be 3 over 75. And then when I add, I get 1 over the equivalent resistance is 28 over 75. Now I don't want 1 over the equivalent resistance, so I'm going to cross multiply. So here I get 75 equals the equivalent resistance times 28. So I divide both sides by 28. And I end up with my equivalent resistance right here of 75 over 28. Okay, and then as a decimal, if you made them into decimals, which you can do, you would still get approximately 2.679 ohms. All right, so if you make them decimals, keep 4 or 5 places up here, and then when you get to your end, keep 3 decimal places. So I'm going to write that up in my picture, okay, the equivalent resistance. Well, actually, I'll redraw my circuit over here. So there's my battery. I'm going to go up, and then I just combined these two. So this is going to be the equivalent resistance here is 2.679. Okay, and then we go over. And then this one, this is just a nice plain old resistor, so I'm just going to go ahead and put that in, 40 ohms. And we go down, and now I need to simplify these two that are in parallel. So, go ahead and try to do that in this space in between here. So again, I need to find the equivalent resistance of these two. So I've got 1 over the equivalent resistance of the 15 and the 18 is equal to 1 over 15 plus 1 over 18. You could find a common denominator, which is how I did it. The common denominator is 90. So 1 over the equivalent resistance is equal to 6 over 90 plus 5 over 90. So 1 over the equivalent resistance is 11 over 90. And then again, we're going to cross multiply. So I get 90 equals the equivalent resistance times 11. Divide both sides by 11. And I get my equivalent resistance is equal to 90 over 11, which is about, it's 8 and 1800ths repeating. So then I can draw up here. All right, I'm simplifying those two that are in parallel to make it a simple circuit, so that the resistance there was about 8.18. And then the voltage here is still 25 volts. So now that I've got a simple circuit, I can solve this like a simple circuit, and then we'll work backwards to find our other pieces. So I'm going to try to grab this and just move it down a little. Nope, not what I wanted to do. Undo that. All right, try grabbing this here. Maybe. I don't think I'm going to be able to do it. That's all right, we'll leave it where it is. So in this simple circuit, we recognize that it's a series circuit. And in a series circuit, to find the equivalent resistance at the battery, all we have to do is add up the resistances. So I've got 2.679 plus 40 plus 8.181818, just put a bunch of them in there. I'm going to keep this to 3 decimal points, so I get 50.861. After we have the equivalent resistance, we can find the current at the battery using Ohm's law. So 25 is equal to the current times 50.861. So the current, 25 divided by 50.861 is 0.492. And now we know in a series circuit that the current is the same everywhere. So I can go around and write 0.492 at all of my components. And now that I have the current, I can easily find the voltage drop using the Ohm's law. So V equals IR. So all I have to do is take 0.492 times 2.679, and I get 1.32, and then 0.492 times 40, and I get 19.68, and then 0.492 times 8.18 repeating, and I'll just go ahead and put a bunch of those in because it's easy to remember, and I get 4.03. Now, I have to go from my simple circuit back up to the complex. So I say, okay, things that look the same, I can just write down. So this battery is the same. So voltage is 25, current is 0.492, and the resistance is 50.861. Also, this 40 ohm resistor is exactly the same. So we have our current of 0.492. and our voltage drop of 19.68 volts. All right, now the ones that don't look exactly the same, I'm going to say, okay, well, those were in parallel. What stays the same in parallel? Voltage stays the same in parallel. So we know the resistance that's given to us. Now I'm going to write the voltage is 1.32 at each of these. And then use Ohm's law to solve for the current. So I've got 1.32 equals the current times 25. So 1.32 divided by 25. I get a current of 0.0528. And then 1.32 divided by 3. A current of 0.44 amps. Similarly with this one, what stays the same in parallel? The voltage. So we take the voltage of 4.03 and put that down for both. And then we know our resistance because it's given to us. And we solve for current. So 4.03 divided by 15.269, and then 4.03 divided by 18.224 amps. So again, when you're solving a complex circuit, first you try to build it into a simple circuit. Okay, so combine things that are in either parallel or they could be in series in other circuits. And then once you have a nice simple circuit, you just solve the circuit like you would a simple circuit. And then to get back, you say what stays the same. If you combine parallel, voltage stayed the same. So you take the voltage and put it down and then just use Ohm's law.